Okay, welcome to the Chapter 1, Part 1 video for Pre-Calculus Honors, where we will be talking about functions and graphs. Specifically, we will be talking about mathematical models, the zero factor property, also called the zero product property, problem solving, grapher failure and hidden behavior, that means when we can't trust our calculators, review of functions and notation, and then some function properties, and if we have time, we might touch on asymptotes and end behavior. Why are these all important? Because models provide different methods to visualize, analyze, and understand data, and functions, including graphs, form the foundation for understanding mathematics and applications. These are the concepts that we need to really truly understand before we can continue forward with this class. Chapter 1 is super important, so make sure that you're understanding this as we go along. The first thing we're going to talk about is models. So we've been using models since we started really talking about algebra way back in 5th, 6th, 7th grade. So modeling is a way of looking at a problem from a different angle. So a mathematical model is a structure that approximates phenomena for the purposes of studying or predicting behavior. We have different types of models, 3 of which we're going to take a closer look at in this class. We have a numeric model. That's a type of model that looks at numbers or data in order to understand something clearer. So when you're looking at lists of numbers, that would be a numeric model. We have an algebraic model, and that's when we write equations or expressions, when we're looking at comparing things that might have variables. So when we're using formulas or looking at quantities with respect to variables, those are algebraic models. And then we have our graphical model. That one's a little bit easier to think of right offhand. That's when we have graphs, but it also means other types of imagery. So when we draw a picture, anytime we're drawing a picture in order to understand a problem, that is a graphical model. You can also say graphic model, but graphical model is more common. So let's take a look at a model. Here we're given a list of data, and so that makes this a numeric model. So we're going to start by remembering how we can use this data in order to find out information. So one way is to look at the data and look at how the numbers are relating to each other. On table 1.2, we see the fluctuation of the number of commissioned officers on active duty for selected years from 1965 through 2015. Is the proportion of female officers increasing over time? So in order to find out if the proportion of female officers is increasing over time, what we need to be looking at is we need to look at the number of female officers, and we need to look at the number of total officers. So we're looking at this number in the female column along with the number in the total column. And we want to compare those. And so I've added a column here, the percentage column, that we're looking at what percentage of females make up this total number of commissioned officers. So to calculate this, we would do 4 over 102, turn that into a percent, and we would get 0.039 which becomes 3.92%. We're going to do that for each of these. I'd like you to go ahead and pause the video to fill out your percentages, and then I will resume the video and fill in that percentage column as well. Okay, so go ahead and compare your percentages to the ones that I got here. And again, that's just each column, female divided by total, and then turning it into a percent by multiplying by 100. So the question was, is the proportion of female officers increasing over time? Because of that word proportion, we know we have to look at the comparison. So we found the percentages. Is it increasing over time? Yes. If we look at the trend, generally it is increasing over time. Each percent gets higher and higher as we go down the list. So now what we want to do is create a scatter plot with the percentages, and we want to see what type of model this is. So if you'll remember back to last night's homework, in order to create the scatter plot, we're going to have to put this information in the calculator. But what information do we want to put in? Well, I would like to look at the trend of female officers over time. So we want the year That can be our X column, our first column. And we want the percentages, that can be the Y column. And you're gonna go ahead and put this into your calculator and try plotting it as a scatter plot. Okay, what type of model is this? Well, once you have the scatter plot, you're looking at it on a graph. So this becomes a graphical model. I had like a pen hiccup here. Graphical model. How do we find an algebraic model? So we had a numeric model that was given to us. We found a graphic model by making the scatter plot. How do we find an algebraic model? Well, remember in that same video going over how to make a scatter plot on your graph, we can also find the regression, the linear approximation. And so we can look at these data points and we can create that linear approximation. I'd like you to go ahead and try it on your calculator, and let's see if we get the same answer. So here you should have what would round to, remember we're rounding to 2 decimal places for these. We should have y equals 0.033x minus 635.75. Now, because we rounded, if we graph the line that we've rounded, the line that I've written here, and not the exact line which you probably saved and looked at the graph of with your scatter plot, we'll see how much rounding actually impacts our data. So because we rounded this, it's actually not going to be very close to our scatter plot. However, if you use the exact numbers from your calculation in your calculator, you'll see that it goes directly through those points, right in between them. Okay, let's look at another example. We'd like to compare pizzas. So we have a pizzeria selling rectangular 18 by 24 inch pizzas for the same price as its large round 24 inch diameter pizza. If both pizzas are the same thickness, which one gives you more pizza for the money? So I'm gonna start by saying, I'm comparing two pizzas, let me draw a picture. Anytime you're saying, let me draw a picture, you're creating a graphical model. So here's my first pizza. It's a rectangle, 18 by 24. My second pizza is round with a diameter all the way across of 24. So how do we find out which has more pizza? Well, now we're looking for surface area. So to find the area of a rectangle, that is length times width or base times height. I'm taking those two perpendicular dimensions and multiplying. 24 times 18 should give us 432. Our units here are inches, so that's squared inches. Sorry about the handwriting. Our second pizza is a circle, but the diameter is 24. In order to find the area of a circle, I need not the diameter, but the radius. Our radius, half of the diameter, is 12. Area of a circle is pi r squared. So that's pi times 12 squared, which is 144 pi. 144 times pi estimates to 452.4 square inches. So which one is bigger? The round pizza. The round pizza gives you more for your money. Okay, one more example here. Oh, the example comes later, sorry. First, we want to review the zero factor property. So for the zero factor property, we're saying that if I have any two numbers that multiply to 0, one of those numbers must be 0. The other way of saying that is if I have a number that is 0 times anything, the product will be 0. So that's what the zero factor property says. And the way that we use the zero factor property is in order to solve for equations with a degree higher than 1. So what I'm looking at is this equation has an exponent of 2. And what that tells me is that in order to solve this equation, I need to set it equal to 0. Everything on one side equal to 0. It doesn't work if it's equal to anything other than 0. And then once we have it set equal to 0, we can factor. If it's not factorable, then remember we have the quadratic formula, or we have completing the square. So in this case, it's factorable. We factor it into x minus 3 times x plus 2. If you'd like a review on factoring, we can absolutely do that either during office hours, or if enough people want it, then we can do an example during class as well. And then we're going to use the zero factor property, which says if these two quantities multiply to 0, so I have x minus 3 times x plus 2, they multiply to 0, then at least one of them has to be 0. So then we say, well, what if it's the first one that's 0, and what if it's the second one that's 0? And that gives us two possible answers. And so we end up with x equal to -2 or 3. Now it can't be both at the same time. I can't have a number that's both -2 and 3 at the same time. So that's why we use the word or. Even though they're both answers, the word or just means x can only have one of those values at a time. Okay, so let's look at that example that I had mentioned earlier. We want to solve this algebraically. Find all real numbers x for which x squared equals 8 minus 4x. Well, this is an algebraic model. Okay, we don't know what it's modeling. We don't have the information about what it's modeling, but we do know how to solve it. And so because of the degree higher than 1 here, I know I want to set everything equal to 0. So I'm going to minus 8 plus 4x minus 8 plus 4x on each side of the equation. Can cancel those out. And I'm going to write it in descending order, meaning the highest exponent goes first, x squared, then our next highest, which is x, minus 8 equals 0. Now the question is, does this factor? Well, in order to find out if it factors, I want to take -8. That's what they need to multiply to. And what do they need to add to? They have to add to 4. Do I have any two numbers that multiply to -8 and add to 4? Factors of -8 are 1 and 8, 2 and 4. None of those have a difference of 4. So it doesn't factor. So what do? Well, we need the quadratic formula. X is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. A is 1, b is 4, and c is -8. So now I'm substituting in, that's -4 plus or minus the square root of 4 squared minus 4 times 1 times -8 all over 2 times 1. So this gives us -4 plus or minus, that's 16 plus 32. 16 plus 32 gives us 48. Divided by 2, 16 plus 32. The square root of 48, that's 4 times 12. 12 is 4 times 3. So that reduces to -4 plus or minus 4 times the square root of 3 over 2. Well, the good news is I can factor out a 2 from my numerator. I cannot cancel the 4 and 2 because of this plus sign here. So because I have a plus or minus, that makes this multiple terms. So I can't just cancel the 2 with the 4, but I can reduce everything. So that makes this -2 plus or minus 2 times the square root of 3. So that gives us our x values. Now, if you estimate this in a calculator, the plus and the minus as two separate values, we get an approximate value of -5.46 and 1.46. So this would be exact, and this would be approximate. Okay, let's take a look at our next slide here. So next we want to look at our fundamental connection. We just solved an algebraic expression or an equation, and we got an answer. That answer we call a solution, okay? And then we can also call that answer a root. Now, where does that come from? Well, it comes from actually the graphical interpretation of this same problem. So if we were to think back, we solved that equation, we got two answers. If I were to graph that equation as a function, those two answers are the x-intercepts. And so we have this connection that when we solve something algebraically, we're also solving it graphically. We're getting information in both models. And so we have a root or a solution when we solve an equation algebraically. We can also call that the zero of the function of that same equation. And we can also call that the x-intercept of the function if we graph it. So the x-intercept is a point. The root or the solution or the zero are all values. They're all the same thing. So all four of those words refer to the same concept. So let's take a look at when can we not trust our graphing calculator, right? So we just solved something algebraically. We could have solved it graphically by calculating the zeros. I want to know, when is it that I cannot trust my calculator? So let's look at the graph of 3 divided by 2x minus 5, that whole quantity in the denominator. And this is what your graph should look like. Now, depending on your model of calculator, you may or may not see this line right here going between kind of the arms of the graph. So what's the difference between seeing it or not seeing it? Well, let's test if that zero exists. See how it's crossing through the x-intercept? That means that it should be a solution to our equation. So we should be able to solve this. We should be able to substitute y for 0, right? The y value at that point is 0, and then we should get a true statement. So let's try it. Solving algebraically. Check. Algebraically. So that means 0 equals 3 divided by 2x minus 5. Well, then in order to solve this, I can multiply both sides by the denominator. So 0 times 2x minus 5 equals 3. Well, 0 times anything is 0. And does 0 equal 3? No. So that is not a 0. That is a false point. This is a false statement. So what's happened is that our calculator has accidentally drawn this vertical line. And the reason that the calculator has accidentally drawn this vertical line is because that is what's called an asymptote. An asymptote is a line that the graph approaches but never touches. It never creates a point on that value. And so the calculator doesn't know how to interpret that. Now, the newer calculators are a little bit better at interpreting it. So if you have a TI-84 Plus that's from a few years ago, it might show you that line. And if you have a TI-84 Plus from this year, it might not show you that line. Okay, so it's not about having the newest, most expensive technology, but it's about knowing how to use your technology. So when you see these graphs, it's always a good idea to be able to know, what do I expect it to look like before I put it into the calculator? And we are going to learn how to graph that equation by hand. But before we can graph that, we need to remember some properties about functions. So let's take a look at a few properties that hopefully sound familiar, such as the vertical line test. The vertical line test is when we check that every x value has only one y value on a graph. And that's what tells us whether something is a function. And when it's a function, we can write it in the form y equals something with only x's. And if x is our only variable, we call it a function of x, or f of x. And so when we're looking at a function, we should never have an x value repeated twice unless it has the same y value. So I can't have, for example, the point 2, 7 and the point 2, 3. That would make something not a function because the x value was repeated twice. Those 2 points would be directly vertical of each other. It would not pass the vertical line test. So those are all ways to tell if something is a function. When we have a function, we have these properties called domain and range. When we're looking at the domain, we're looking at all possible x values on a graph. So let's just say that this is my graph. Because it's going off to the side, and I have this line that makes it look like it's going, and it keeps going up in this direction, all possible x values would be if I take my graph and I move all of these directly to the x-axis. Every point would be filled in. If I took the graph and I smushed it like a sandwich, like a panini, directly down onto the x-axis, all of the points would be in. That's the domain. Now, sometimes the domain doesn't have all of the points, and we've seen some graphs where that's not the case. We'll talk about that in more detail later. The range is when I do the same thing, but on the y-axis. So I'm taking the point, every point on a graph, and I smush it over to the y-axis. Now, because this graph goes off along this x-axis, doesn't look like it's ever going to pass it, our range would be limited. So our range would be from 0 to infinity on this graph. Okay, so we can find domains and ranges. The way we find domains is we look at what cannot happen algebraically. We can't divide by 0. We can't take the square root of a negative. For the range, we can do something algebraically. We'll get to that towards the end of next semester. For now, we will look at finding them graphically. Okay, we can also say that the domain is the x's, those are the independent variable, and the range is the y values, and that's the dependent variable. Okay, and lastly, for our domain and range, we could have implied restrictions. We've seen this before where you have distances that have to be positive. So even if I have, for example, a function that could have negative values, if it's a distance, I know that those negative values can't actually happen. That's an implied restriction. Not a mathematical restriction, but a restriction on the situation. If I'm running a certain distance, I can't have negative distance that I'm running. Okay, so things like that are implied restrictions. So let's practice finding the domain of a function. In order to find the domain, remember we had 2 restrictions. We cannot divide by 0, and we can only take the square root if it is not a negative, so positive or 0. So that means I have to look at this function and say, could I ever divide by 0? No, there's no variables in the denominator, then we don't have to worry about that. Could I ever have a negative inside of a square root? Yes. So what we're looking at is we need to take what's called the radicand, the number inside of the radical, and we have to say that always has to be positive or 0. How do we say that? The radicand always has to be positive or 0. Greater than or equal to 0 will take care of that for us. So when we're looking at the domain, if we have a radical, we set it greater than or equal to 0. And then we solve, so subtract 3 from both sides. X has to be greater than or equal to 0. Okay, that is our domain. We can write it as the inequality. If I wanted to write it as an interval, interval would be from 0 to infinity. 0 is an answer, so I put a square bracket around it. Remember, square bracket means included. A curved bracket means not included. I always have a curved bracket around infinity because infinity is not a number. It can never be included in my number set. And lastly, I could write this as a set x where x is greater than or equal to, I'm sorry, this, I said 0 minus 3 was 0. 0 minus 3 is not 0, negative 3. So x has to be greater than or equal to negative 3. So we have our inequality notation, our interval notation, and our set notation. We can also solve this graphically by looking at the graph. Go ahead and try graphing it on your calculator, and I'll put the graph here on the screen. So if we look at this graphically, we can see that the graph has the smallest y value, right? Or sorry, the smallest x value, the domain is the x values. My smallest x value is at -3. And then I can fill in, every single one of these points would fill in the x-axis all the way out to infinity. And so from this graph, we can also say that the domain is from -3 to infinity. Now that method where we look at the graph and we say, what would happen if all of the points were on the x-axis? Where are all of my points? Is the same way that we'll find range. So let's take a look at the range in the next problem. So in this example, we want to find the range of a function. In order to find the range, the first step is to graph it. Go ahead and try graphing this, and then I'll put the graph up on the screen. Okay, so here's our graph of the function. In order to find the range, we're looking at y values. So the question is, where are my y values? Well, y values are the points going over to the y-axis. So imagine taking this and smushing it between your hands sideways. All of these points would end up on the y-axis, right? They're all kind of going towards, and the y-axis is pulling them towards itself so that we can see where are all of my y values. Well, notice all of these points fill in the entire axis, except there's this gap, there's this discontinuity. And that discontinuity happens at 0. We're going to talk about discontinuity again in just a couple of minutes here. But discontinuity is when we have to pick up our pencil in order to finish drawing the graph. You cannot draw this graph without picking up your pencil. And what is the point where you have to pick up your pencil is at 0, the y value of 0. You can't draw the graph through the y value of 0 without picking up your pencil. And there is no point with a y value of 0. And that means that our range has all of the points except 0. So it goes all the way up to infinity. It stops at 0, resumes at 0, goes down to -infinity. Always writing this from least to greatest, smallest numbers first. -infinity is our smallest number. So our range goes from -infinity to 0, stops. So not a bracket, but a parenthesis. And then it picks up, so we say union. We're picking back up, again, a parenthesis at 0, all the way to infinity. There are no square brackets because 0 is not included in our range. 0 is a hole in the graph. Okay, so I had mentioned continuity. Let's take a look at what continuity is. The question for continuity is, do you have to lift your pencil up in order to draw the graph? If I don't have to lift my pencil up, so that first graph there, that means it is continuous. Imagine these all have arrows on them. The textbook doesn't put arrows on the end of all of its graphs. So all of these have little arrows on them. Okay, so then do I have to pick up my pencil? No. Where do I start? Where do I stop? Well, I started, because of that arrow, at -infinity, and I stop at infinity. So it's continuous on all of x. It is continuous. CTS stands for continuous from -infinity to infinity. Okay, in all of our other 3 examples here, you have to pick up your pencil at some point. But the question is, how much do you have to pick up your pencil? So in our first example here, it just skips over 1 point. Skips over just that 1 point right there. I could fix this by just coloring in that dot, and then it would be continuous. If that's the case, it's called a removable discontinuity. If I can fix it by putting just 1 point, it is a removable discontinuity. If I have to draw a segment in order to connect my 2 sides, and let me actually use a different color here. If I have to draw a segment in order to connect those 2 sides, that is a jump discontinuity. There we go. That is a jump discontinuity. And our last type of discontinuity is if the 2 sides of my graph are heading off in opposite directions. this one's going down, this one's going up. That is an infinite discontinuity. And we draw a little dotted line between the two sides, and that's how we denote that infinite discontinuity. That little line that we draw is called an asymptote. I'm going to have that word typed out for you in a few slides. An asymptote. We saw it earlier when we were looking over the plan for the lesson. Okay, and that asymptote is like a wall. The graph does not cross that wall. There is one case where the graph can go through an asymptote, and we'll talk about that next class. Okay, so I'd like you to think about that list of 12 functions that we started talking about in class. Which of those functions have discontinuities? Okay, we'll talk about that later as we fill in the chart. So let's look at identifying points of discontinuity. This is a try this. I'd like you to try it, and then I'll do an example. Draw a function that's discontinuous at x equals 2. So that means we need to first think of a shape, draw it, but make sure that you have to lift up your pencil at x equals 2. So I'm going to start and I'm going to say, let's try an infinite discontinuity. Remember, an infinite discontinuity means the ends of the graph go opposite directions at our point of discontinuity. So when x equals 2, I'm going to draw that line where x equals 2. And I'm going to say, I want my graph to go off in opposite directions. I'll have one going up and I'll have one going down. There is a graph that is discontinuous at x equals 2. You could also have chosen to do a jump discontinuity. If this is 2, I can have a graph that goes like this. And then remember, I want this to be a function. So if one point is filled in, the other point should be hollow. Or I could have done a removable discontinuity. I could do something like this. And then where x is 2, I put in a hollow circle to denote that that point is discontinuous. Okay, I have a challenge problem there. If you feel like you understand discontinuity and you'd like to take a challenge, I challenge you to write an algebraic function that is discontinuous at x equals 2. So any of these different types of discontinuity, but can you come up with a function that is discontinuous at x equals 2? Another property that we look at with functions is whether they are increasing or decreasing. What that tells us is if they're getting bigger or smaller. Their y values are getting bigger or smaller. So this is just another way of asking if the slope is positive or negative. And then we also have the possibility of a slope of 0, and that is called constant. And so our first image here, we have a positive slope. It is increasing. Positive means that it is increasing. Every single point here, the next point to the right of it is above it in some way. If we have a negative slope, the points are going down. Each point to the right is below the previous point. That is decreasing, negative slope. And then our other option is if the slope is 0, they're not increasing or decreasing, they're staying the same, constant meaning the same, then we would have a constant slope. We would have a constant function. And then we can have combinations. We can have parts of a graph that are increasing, decreasing, and parts of a graph that are constant. So in this graph, we have the graph is going down and then it stops. So at -2, it switches from decreasing to being constant. And then it's constant until +2, where now it is increasing. Notice that the endpoints are included in our intervals. This was decreasing from -∞ to 2. It stops decreasing at, or -2, stops decreasing at -2, but we include it in the decreasing interval. We will include the endpoints in the constant interval, and we will also include the endpoints in the increasing interval. However, infinity and -∞ can never have a bracket because they're not a number, they cannot be included. Okay, our last property that we're going to look at today is, well, let's do an example. I got ahead of myself. Okay, so our example here for increasing and decreasing behavior is a function. This is a double absolute value function, but then I simplified it out. So we have three cases. F of x is -5 if x is less than -3. F of x is 2x plus 1 if we're between -3 and 2. And then f of x is 5 if we're greater than 2. So what is happening? First, let's draw a picture. Graphical model. So my x values that are my kind of breaking points are at -3 and 2. That's where I'm going to start. Here is -3. Here is 2. What's happening to the left of -3? If x is less than -3, then f of x is -5. Here's -5. There it is. There is my function. That is constant. The slope is 0. The x value is staying the same no matter what my y, or what the y value is staying the same no matter what my x value is. And then we have between -3 and 2, the graph of 2x plus 1. So here's plus 1. If I follow my slope, it will connect there, and then it will keep going all the way and stopping at 2. Should be a hollow circle around my filled in circle. Okay, so these two endpoints are hollow. This endpoint is filled in. This endpoint is filled in. How can I tell? Because of that equal to sign. Our last part, if x is greater than or equal to 2, starting at 2, then my y value is 5. There it is. Now, hopefully you're doing this on graph paper. It'll be much easier to see if you're doing it on graph paper. So I want to identify the intervals for which it's increasing, decreasing, or constant. So let's start with increasing. Increasing means a positive slope. It's increasing from -3 to 2. Is there any other place where it's increasing? No. We can look at the whole graph and we can see it won't be increasing anywhere else. Decreasing means a negative slope. Is there anywhere that the graph has a negative slope? There's nowhere that the graph has a negative slope. This symbol means empty set, no solution. There's nowhere that the graph has a negative slope. And then we have constant. Where's the graph constant? Well, it's constant all the way to the left, but also all the way to the right. So how do we write that? Well, from -infinity to -3, including the endpoints, but also from 2 to infinity. When we have two pieces with a gap in between, we put a union sign. So that's -infinity to -3, union. I should keep writing, but I had ran out of space. To my pen doesn't like writing down there. Hold on a second. Let me see if I can change that. To infinity. Okay, sorry about that. So we have increasing, decreasing, and constant. Okay, now our last property here. So boundedness. Boundedness I think of as, can I make the function into a sandwich? Can I put a piece of bread below it? Can I put a piece of bread above it? Why do I like bread for this example? Because bread is kind of fragile. If I'm a function, I can break through bread really easily. So in this first example, we're looking at a graph that both arms go up. And therefore, there's going to be some point below the graph where the function won't cross that point. And that is called a lower bound. So that red line underneath our graph here is called the lower bound, meaning it can go underneath the graph and the graph will never cross it. However, I can't put a piece of bread above this graph because if I tried to put it here, it would break through. And if I tried to put it higher, those arms are always going up, so it will keep breaking through. The same thing happens if I can put a piece of bread above but not below. So I can find a point that's above every other point in the graph, but I can't find a point that's below every other point in the graph. No matter what, if I keep going, I will keep finding points on the graph that are below my line. So that would be just bounded above. It has only an upper bound. And then we have the case where we have, we can put kind of sandwiches above and below. And this would be like sine or cosine, a graph that's oscillating, okay? So this has a bound above, an upper bound. It also has a bound below, a lower bound, and therefore it is bounded. It has both, then it's bounded. If it only has one, it's not bounded. It is either bounded below or bounded above. And then we have the case where we can never put a bound. It will always go through the graph, and no matter where we put it, there will be a point above and below that point, and that is unbounded or not bounded. So how can we think of boundedness relating to range? Well, if my range has an endpoint, my y values have an upper or a lower bound, there's going to be a point where my range stops. Okay, so think about that and think about how you can interpret that to make it easier to understand boundedness. And along with boundedness, we can find what are called extrema. And extrema are the points that are the bottom and top of a graph. So, for example, in this graph here, we have a lower bound below the graph, which means that I should find a point that is the lowest point on the graph. So if I have something that has a lower bound, then that means there should be a lowest point, and that lowest point is called an absolute minimum. It's the absolute smallest we get on that graph, the absolute minimum. There might be some points that kind of fake you out. They say, oh, I'm lowest, but not on the whole graph, just in an area. And that would be called a relative minimum. It's like, oh, I'm the lowest point, just kidding. It dipped down even farther again. So this would be a relative or local minimum, and this would be an absolute minimum. And then we have this idea that, oh, well, then I can do the same thing for the top. So I have here an absolute maximum, or I can have a relative or local maximum. And that means that I'm the highest point on the whole graph, absolutely the highest point, the absolute maximum, or I'm the highest point, but only on part of the graph, relative maximum. Not all graphs have extrema. They don't all have maximums or minimums. So this graph here shows an example of it's always, always, always increasing, and therefore it's never going to have a maximum or a minimum. It's always increasing. So there's never going to be a turning point where we hit a maximum or a minimum. Okay, I'd like you to try this example where label the red points as either maximum, minimum, relative, absolute, or none. And then we'll go through it together. So this point here is an absolute maximum. It is the top of the graph. There's nothing higher than that. This point here is an absolute minimum. This point, it's not the top of anything, it's not the bottom of anything. This is neither. Okay, now if you interpreted this as that the arms of this graph keep going up like this and down like this, then you would change these absolutes to relative or local. Relative and local are synonyms for each other in this case. Okay, let's do one more example and then we'll be done for the day. and that is an example in identifying extrema. So we want to find all maxima and minima, those are the extrema, the y values, and the values at which they occur, that will be the x values for this function. Then give the intervals of increasing and decreasing. I'd like you to try this as your example for practice, and then we will go over it together in class.